All right. Hi, everyone. Welcome to our talk. Today, we're going to give you a little bit of a behind the scenes of a new open source library called Phoenix. Specifically, we're going to go into the details of how to unravel embeddings using UMAP and HDBSCAN. But before we get started, let us introduce ourselves a little bit. So my name is Mikio. I'm one of the founding engineers here. I've been working with embeddings for about the last year or so. And Kiko, you want to introduce yourself?
Sure. So thanks, Mikio. My name is Kiko. I've been working here at Arize for 2 years as a software engineer and data scientist. I've been mostly focused on the embeddings product, both from a research standpoint and an implementation standpoint. So happy to be here telling everybody about it.
Cool. All right. Well, we're very excited to show you what we have today. But first, let's kind of reset the stage, talk about what is ML observability. So it might be, common for people to know about how to deploy models, how to monitor them. But machine learning observability is not just simply the process of deploying your models and monitoring how they're doing in production, but it actually speaks to a larger practice of surfacing up problems you see in production, identifying problematic areas or cohorts that are drifting or performing badly, reincorporating this data and retraining your model to account for those identified issues, validating that these changes are working, and updating your model and continuing this cycle. This process of keeping your models in production performing well is what we call machine learning observability. So here at Arize, we want to provide the best tools for every environment. In particular, we want to bring some of the great features that Arize offers and make them easily accessible via a Python notebook for faster iteration. In addition, we thought it would be paramount to make this project open source from the get-go so that more of you can benefit from some of our findings. Our new open source library is called Arize Phoenix, and it is specifically targeted for providing machine learning observability in the notebook. It's well suited for models that deal with unstructured data, such as computer vision, natural language processing, but also normal tabular models can benefit from this as well because we have convenient embeddings generators as well. And lastly, Phoenix has a built-in support for large language models in the forms of prompts and responses. But before we get too into the details, let's talk about how Phoenix specifically solves some of the MLOps problems in the notebook. So one, Phoenix is great for detecting embedding drift over time, how your production data is shifting from what it was trained on. It also helps you analyze how your model is performing via an interactive UMAP point cloud. We'll go into the details of this in a little bit. It also helps us identify clusters of inferences that are drifting and performing badly. Phoenix is also great for resolving problems. It identifies badly performing features and prompts. It allows you to export data for fine-tuning, and it helps you leverage problematic embedding clusters for steering vectors and to use them for monitoring. But before we go into the real details of Phoenix, let's go into embeddings so that we all are on the same page. So what are embeddings? Embeddings are a series of floats in the form of vectors. However, they're a very specific type of vector where the distance between the vectors encodes a semantic meaning. So what do I mean by this? The analogy I like using is color. So color is very often represented as RGB, or red, green, and blue. So it's a vector that represents the amount of red, the amount of green, and the amount of blue used to create a color. What makes RGB vectors meaningful is that if colors are more similar, they're actually closer together to each other. So for example, turquoise and blue would be closer together in the 3D projection, as well as things like white and black, which are opposite, would not be as close to each other, or actually on the complete reverse sides of the spectrum. Since RGB deals with 3 dimensions, it's pretty easily represented as this 3-dimensional cube of colors. But embeddings that are used in computer vision and natural language processing models deal with many more dimensions, and thus are much harder to visualize. Take this example of this embedding on the right, which represents how a machine learning model might encode words. So one word might represent a man, another might represent a woman. And the dimensionality of these embeddings is much higher than that of color. But similar to the way that we had with color, distance encodes a semantic meaning. So queen would be similar to king, and woman would be similar to man in the vector space that is these embeddings. So how do we start troubleshooting such a model? One thing we might want to track is embedding drift, to track whether or not our embeddings seen in production are drifting from what we are trained on. So for an explanation of embedding drift, I'm going to hand it off to my colleague, Kiko.
Yeah. So as Miki was saying, the idea here is Phoenix and Arise, we have an approach which is temporal. So we want to target points in time where you might have problems. And that in itself is very valuable because it's pointing you, is partitioning your data in different points in time instead of having to look at your data as a whole. So once you look at the data at a point in time, how do you know what even is embedding drift? So what we do is take these points, these vectors in high dimensional space. You think of 1,000 dimensions, even 10,000 dimensions. So things that we humans cannot even comprehend. So what we do is to take these clouds, these many points, many vectors, from comparison from baseline to a primary data set, and we see how this distance evolves over time. Think differences in magnitude, or think differences in angles. So as your embeddings, which are representation of your data, as your data becomes different over time, you can see this graph increasing. So if you now look at different points in time, you can target different problems and know when to spend your time debugging. Uh, Now, after you've done this, you've located the point in time that you are interested in, and there's possibly a problem. What do you do from here? So I'm going to let Mikio continue on what to do from here.
Thanks, Kiko. So that's exactly right. So embedding drift over time, specifically Euclidean distance over time, can identify pockets of time that you might be experiencing drift. But after that, what do you do? Since embeddings are in this really high dimension, it's pretty hard to reason about embedding drift or even understanding your model. So here we have an analogy of, for Nintendo, they use a simple dimensionality reduction technique to project from 3D Mario into 2D Mario. While this might work for Nintendo, it doesn't actually work for our embeddings. The reason being is that we actually lost some information when we projected from 3D Mario into 2D Mario. What's not so obvious, maybe, is that the backside of Mario is lost, and we actually lost some information. And so while this might work for Nintendo, this doesn't actually work for machine learning models. So when you are going from a higher dimensional space to something that's easily understandable for humans such as ourselves in 3D and 2D, we need a specific algorithm that's able to preserve the semantic meaning that is in the distances. And in order to do this, we have a very specific dimensionality reduction algorithm called UMAP, which stands for Uniform Manifold Approximation and Projection. And to give you a little bit of the details of the strengths of UMAP, I'm going to hand it back to my colleague Kiko.
Yeah, thank you, Miguel. So as you were saying, the need here is for us humans to understand our data, and we can only visualize 2 and 3D. If you count colors, that's maybe a 4 dimension, but if we don't count colors, it's 2 and 3D. The difficulty here is, how do I get an accurate and honestly meaningful representation of my data in these lower dimensions when the original dimensionality is in the thousands? The good news is that even though the dimensionality of the data can be in the thousands, the meaningful part can live in somewhere of a subspace of that. The difficulty is capturing it. So we have algorithms, dimensionality reduction algorithms, and UMAP is one of them. Specifically, is one of the type of neighbor graphs. There are many types of algorithms in terms of dimensionality reduction. We are interested in neighbor graphs specifically, and we chose UMAP for a series of reasons. First reason, it would be that it's really good. It's notably good at preserving both global and local structure. And we have another talk that we go over this. The way that we balance what is important to us as scientists or as engineers between global and local structure, we can balance that and what is important to us with the hyperparameters. So we do have a really good balance there. We can see both, we can see one, or we can see the other. Another reason is that it's really exceptionally good with nonlinear data. And without going too much into it, like most of the data out there is nonlinear. It would be an anomaly that it was. So this is a non-negotiable. It has to behave well with nonlinear data. Um, Another good aspect of UMAP is that it's relatively fast. I mean, it's not fast in itself. I mean, it's not the fastest algorithm, but within the family of neighbor graphs, it's notoriously for being fast, and it's scaling really well. So if neighbor graphs is what you want to do, UMAP is an excellent choice in this regard. Lastly, robustness of parameters. What this means is that UMAP, as I said, there are knobs and configurations that you can edit, and imagine how difficult your work would be if you change whatever hyperparameter from 2 to 3 and the whole UMAP just changed completely and it went completely different. Then your life will be miserable because you need to change something. Like with a little bit of change, the difference will be dramatic. So gladly, UMAP does not behave this well. You can, as long as you hit a given neighborhood of hyperparameters, you're going to get mostly the same, and you can edit and iterate much easier than if the differences were dramatic. So for these reasons, UMAP is very desirable. As I mentioned, we are mostly interested in neighbor graphs, and the reason for that, again, in a overall manner, is because it captures the essence and relationships of the different data points and vectors in high dimensions and tries to place them into lower dimensions. So, yeah, with this, I think I'm gonna hand it back to you, and yeah, I hope that this helped everybody.
Cool. Yeah. So UMAP is really great for without having to know too much upfront about the structure of your data, really being able to deep dive into your models in low dimensional space. So Kiko kind of alluded to it. We're, as humans, kind of limited to 2 and 3 dimensional space, but we have actually one more dimension at our disposal, and that's actually color. And so one thing that we can do with UMAP is color the points by certain labels. Specifically, when you send in inferences to Phoenix, similar to Arize, we capture all the features, all the tags, along with your predicted values, as well as some ground truth information off of which we can calculate evaluation metrics. And what we can do is actually color the point cloud by these different dimensions. So whether or not it's features, say you have a submarine taking some pictures of the ocean floor, maybe you would use something like depth to color the point cloud. Maybe you have a ranking model and you have a confidence score that you want to ingest. We can also map a color range between low confidence and high confidence. And third, we can actually calculate different evaluation metrics and color it by things like the confusion matrix. Did your model predict the right value? Is it a true positive? Is it true negative? To give you a little bit of a visual illustration, I'll give you some examples. So Phoenix built-in has color by dataset. This is great of splitting your data into whether or not it's production or the baseline dataset, being able to identify pockets of drift. We also have things like color by correctness or color by confusion metrics, which lets you isolate different areas of correct predictions and incorrect predictions. And we also have things like color by feature or tag or prediction that lets you introspect the insides of your model in a visual way. Okay, so now we projected things into 3D and we want to better reason about our model. Well, sometimes if you're dealing with 2,500 points, it's kind of hard to reason about things in chunks. So clusters is something that we've introduced in Phoenix. And clusters are areas of high density that can be analyzed for common or sometimes uncommon characteristics, depending on what you're looking for. Since distance encodes semantic meaning, clusters provide a good unit of data or a primitive by which you can analyze your model, things such as feature drift or performance degradation. So similar to the way that you can use statistical binning, like deciles or quantiles, to kind of map out your more tabular data, clusters provide a way to split your data into groups that help you reason about your embeddings in higher dimensional space in kind of a reasonable way. With Phoenix, we use a very specific clustering algorithm called HDBSCAN. HDBSCAN, it stands for Hierarchical Density-Based Spatial Clustering of Applications with Noise. And for the strengths, I'm going to hand it back to Kiko.
Thank you. So this is honestly one of my favorite algorithms out there. So I'm very excited to tell you about it. Um, let's start. As Mikio said, it's the HDBSCAN is basically giving you what it does in it's part of its strength. So if I'm gonna go out of order, but uh, I want to order it this way. So spatial clustering is basically mentioning that is clustering points or grouping points that are similar to each other in the space. Now, what does it mean to be similar and being close to each other? Embedding vectors encode similarity by the distance. So points that are close to each other are similar, points that are far away from each other are dissimilar. So you can imagine that we want to understand regions of the space where possibly we have, if it is a computer vision classifier, we have dogs, or regions of the space where my model is doing poorly. Now, density based is that as these points get together, they increase the density of points in this region. So if you think of a little region of the space, the more points that I have in that region, the higher the density. And what HDBSCAN is really good at is to find those regions and telling you about it. It accounts for noise. So what this does is think of the noise as your quality control. What this means is that if, like other clustering algorithms, they are forced to cluster all the points. Every point must be assigned to a cluster. And you can think of many data sets that, for instance, they have outliers, or it doesn't even have to be such a dramatic case. It could be a point that is kind of in the middle between two clusters. So if you're forced to cluster every point, you're going to see your clusters being kind of weird and not intuitive. When you look at it, you're going to see that point probably out there shouldn't be included in this cluster. Allowing for noise is the way that we tell HDBSCAN, hey, if you don't know where this point should be, just it is okay to qualify it as noise. That way, the clusters what we do get in return from HDBSCAN are of that much higher quality. There is actually settings to make HDBSCAN more or less conservative, so you are totally under the control of this quality control. And lastly, they are hierarchical, and this has to do with the image that you're seeing in front of you. So think of this image is representing, or at least we tried, to the points in the space, and then on the mapping, these mountains are the 3D representation of the density. So think of the hierarchical control as the sea level in these valleys, in sea level that we can cover these islands, or we can lower the sea level and we'll find more islands. So if we lower the sea level, islands are going to appear. So more clusters are going to appear that before we didn't see. If we lower it even lower, maybe a big island with a small island, they can join and have a bigger cluster together. So you'll see as we edit the settings, the two clusters become one. Or you could do the opposite route. You raise the sea level, and suddenly before you had 7 clusters, now you have only 2, and they're small. So you are totally under the control of how many clusters, how big you want to see them. And then for this, we have another talk to go over in detail with clustering. So I'm going to stop it here and give it back to you, Mika.
Yeah, thanks, Kiko. So how do we use clusters? So as we kind of mentioned, clusters provide kind of a grouping mechanism so that you can easily identify different areas of similarity or dissimilarity. And specifically with Phoenix, what we do is first, we run HDBSCAN to find areas of high density. Then 2, we evaluate the drift and the performance of the points within those clusters. And third, we sort your clusters by problematic areas. So in this case on the left, you can see that the clusters have now been sorted by the percentage or the ratio of how much is seeing in production versus training. And we're easily able to show pockets of high density where your model is potentially drifting with regards to embeddings. So let's bring it all together with how this is executed in Phoenix. So first, we talked about identifying moments of drift using Euclidean distance over time. Phoenix automatically splits your data out over time and identifies different peaks and valleys of embedding drift. 2, we take the moment in time that you're trying to evaluate, and we visualize the drift using UMAP to identify structural differences between your data sets. Third, we break apart your data that we saw previously in your UMAP projection, into clusters using HDBSCAN, and we sort those clusters by bad performance. And then fourth, you can introspect the different embeddings within your clusters and export problematic areas for fine-tuning or things like steering vectors. So nothing speaks better than a demo, so let's get to the demo. So I'm going to bring up my Visual Studio Code. You can obviously use Phoenix in whatever Jupyter environment of your choosing, but I've chosen VS Code. So here we have two pandas data frames, one loading in training data set, something that the model was trained on, and then another one in production. Specifically, we're going to look at human actions. This is a computer vision model that takes different images of different humans and tries to predict what classification of actions they're taking. So let's take a little peek into the data frame. So you can see that each record within these data frames contains the URL to the image, the vector representation of the image, the predicted action, so things like drinking or fighting or clapping, and the ground truth target value as well. We have one for production as well, so it's very similar. And here's a little utility function to visualize this within the notebook. So here we can see this woman having a boba tea of some sort at a cafe. Maybe here we have an image of people fighting on a street corner and people clapping at a concert. All right, so Phoenix is pretty simple. You just kind of define which parts of your data frame represent things like predictions and ground truth data or embeddings. Once you have that set up, you can construct data sets from them. And then we actually start running an application for you that kind of runs alongside your notebook that you can interact with. So let's do that right now. Sure enough, now Phoenix is up and running, and we can actually open it in another browser window. So I'm going to do that right now. And now we have Phoenix up and running. It's figured out the schema of your model. It's figured out that you have a prediction dimension. And now we're going to deep dive into the image embedding. So immediately we do what Kiko kind of mentioned, is breaking apart your data over time and figuring out different pockets of time in which you experienced embedding drift. You can see this huge spike here. But before we kind of jump into that, let's explore our model a little bit. So I'm going to hide this panel here. I'm going to take a little deeper dive. And what you'll notice is Phoenix actually has projected both your production data and also your training or your reference data set into the same UMAP projection. And what you'll notice is here we have our production data, and here we have our training data. And you can roughly see that these are roughly of the same shape. And so it is experiencing not too much drift, and we can actually confirm that visually. But you might not quite understand what this point cloud means. So in order to do that, let's change the coloring a little bit. So now I'm going to switch over to color by dimension. I'm going to select the predicted value. Okay, great. So now we can kind of see that the model is predicting different values and mapping those into different spatially into different parts of the UMAP. So let's kind of unhide all these colors and focus in a specific area. So there are images using a laptop. Okay, so it's kind of on that bottom left. I'd assume that texting would be similar to using your laptop, so let's turn that on. Sure enough, using texting and using your phone is in a similar part of the space. Let's take a look at some of these points before we do anything further. So let's circle those values, and sure enough, these all represent images of people using the laptop. Well, what if I want to classify it back by the value that was which data set? Sure enough, I can switch it back, and now I know which ones are in production and which ones are coming from training. Okay, so let's leave it this way. And let's now go, well, there's one other thing that Phoenix can do, which is figure out different pockets of bad performance. So now let's color by correctness, which values that are correct are true positives and true negatives. Bad values are false positives and false negatives. Let's specifically look at some incorrect values. Our model's not doing too well in certain areas. You can see that some places we're predicting that they're eating, but they're actually sitting. It predicted that they're using the laptop, but they're actually texting. So you can kind of quickly identify different areas, and you could quickly export this data, relabel it, and use it for fine-tuning your model. Well, let's identify drift. Okay, so I'm going to now turn on all the data and go back to the dataset view and show my time series. Let's focus back into this high spike. This looks suspicious. I'm going to click to look at the data here. All right, now I'm going to hide this for a better view. So if we toggle these on and off, you can kind of tell that the point clouds are diverging a little bit, but it might not be that obvious where you want to focus in on. So as we mentioned, we've broken apart this space into clusters, areas of high density, and we sorted them by drift. So which ones have more production data than training, specifically areas that are undersampled that you might want to put back into your model for retraining. So let's click on the first one. Whoa, so these images look a little bit different. And this cluster specifically is 39 points that we've only seen in production. I already can kind of tell that something is off about these. And so here we have a bunch of grainy images. This looks like something I might want to retrain on. Let's explore the next one. These are similar. These also have graininess, but let's focus on this one. So now I'm going to click export. And now Phoenix will actually put this data back into your notebook environment. So let's go back to my notebook. You can quickly access the data that you've exported back in the notebook by getting the exports object and getting the last one. So let's look at that. Now we have the image vectors and the images associated with the cluster that we looked at. And let's use that convenient function we had before to display some of them. And sure enough, now we have the grainy images right at our fingertips to relabel and retrain our model on so it can better handle grainy images. So with that, that completes our demo. Let me go back to our slides here. Again, we're really excited that this is open source and something that you can use. Feedback is always welcome. Phoenix is open source at github.com, arizeai/Phoenix. Feel free to drop us an issue if you have any questions. We're also available on community Slack at Phoenix Support. Hope to see you there. Thanks so much.
Thank you, everybody.